Students, good morning all of you. In last class, we discussed about the kinetic energy here. The kinetic energy of a particle executing simple harmonic motion is here. Its form is already derived here. Now, the first one, types of energy. First one is nothing but the kinetic energy. This kinetic energy of simple harmonic motion is on the account of or on the basis of the velocity of a particle. Its equation is here 1 divided by 2m into v square, where v is the velocity of a particle or executing simple harmonic motion, where v is nothing but what? The velocity of particle executing simple harmonic motion. Its equation already we derived here, that is omega under root a square minus of y square, where a is and a maximum displacement, or it is called the amplitude of the particle. Okay. If you substituting this value in this equation, the kinetic energy become what? 1 divided by 2m into v is like this. It is the ultimate square of this all terms. It means that omega square and square of this complete term is root and square gets cancelled. It is only a square minus of y square. Then if you expand the bracket here, 1 by 2 m into omega square into a square, 1 by 2 m into omega square into y square is there. 1 by 2 m omega square into a square. If you taking this one only, this become what? The maximum kinetic energy, because maximum displacement is there. And another one is bracket expansion, 1 by 2 m into omega square into the displacement square. This is the equation of kinetic energy we completed in yesterday class, in last class. Then we have to draw the graph of this one, the graph of the kinetic energy. Now, if you want to draw the graph of kinetic energy, along y-axis taking the kinetic energy, it is a positive and this is a minus. It is a minus, but we already know that what? The kinetic energy or total energy is nothing but the total energy should not be negative, or it never be negative here. Okay, if it is never be negative, I'll draw one x-axis. Along x-axis I'll take only time here. Then I'll draw one more line here. I'll draw one more line which represents the maximum kinetic energy. Which represents the maximum kinetic energy at this point. Okay, from its mean position. Consider this is the mean position. If the kinetic energy become minus, then this is the negative. Okay, otherwise it's not. Then we have to calculate here. This is called the mean position. After at here pi by 2, it is extreme position. Then it reaches the again its position. Okay, we already know that the displacement graph is there. The displacement graph is like this. It is a mean position, positive extreme position, negative extreme position, and this is also considered as a mean position here. Okay, at here the y is equal to 0. Displacement is 0 at mean position. At here the displacement is 0 because it is a mean position. In positive extreme position the displacement is plus a. At negative extreme position the displacement is minus a. It is a maximum at extreme position. Like that, we have to take the y is equals to a, and we have to take the y is equals to minus a, or we have to take the y is equals to what? 0. By using the values of those y's, we can calculate the kinetic energy. First one is at mean position and extreme position. I will take here rightly. First condition, if y is equal to 0, it is what? Minimum. minimum. At which position? At the mean position. Okay. If it is y is equals to 0, then what about the kinetic energy? Substitute the y is 0 here. Substitute the y is 0. If it is 0, 1 by 2 m into omega square into a square only, because the remaining term become what? 0 here. If it is completely 0, then the kinetic energy is equal to what? The kinetic energy is equal to 1 divided by 2 m into omega square into what? A square. You can take this one. You can take this one. Next, another one is, next part is, if y is equal to a, it is plus a. It means what? At y is equal to 0, at mean position y is equal to 0, the kinetic energy is with the maximum displacement, so the kinetic energy is the maximum here. It means it starts from not here, it starts from here. The kinetic energy is maximum at mean position. At mean position, the kinetic energy that is maximum. The kinetic energy is maximum. Its equation is 1 divided by 2 m omega square into a square is there. At this position. Next, another one is, I'll write all things here. It is pi by 2 or it is t by 4. Time taken. Time taken I will take here. T by 4 and is t by 2 and this one is 3t by 4 and the one is t is that. Okay. Then if it means what? Extreme position, y is equal to a, this is the maximum, then what about the kinetic energy? Substitute the value of y is equal to a in this equation become what? Y is equal to a means it become 1 by 2 m into omega square into a square. Under one same term is there. It means 1 by 2 m into omega square into a square minus 1 by 2 m omega square into a square. Then these two gets cancelled. If these two gets cancelled, then what about the kinetic energy? Is 0. Now the kinetic energy is minimum. It becomes 0 but never become what? Negative. It become what? 0 here. Like this. Okay, like this. The next one. The next thing is, if the y is equals to again what? Negative. Here the y is equals to what? Negative is there because negative extreme position is there. Then y is equals to, first it is reaching like this. That graph of y is like this. Okay. It is 0 plus a and it is 0 and it is minus a. Okay. First then it is 0. 0. Again it is what? Minimum. Again the kinetic energy is equals to what? Maximum. 1 by 2 m into omega square into a square. Again it is a maximum. Maximum means what? From here it is what? The maximum, like this. Okay. Then the next one is, if y is equals to minus a, y equal to minus a, it is also maximum in negative direction. Maximum in negative direction. So that kinetic energy equals to what? See here. Y is equals to minus a means minus a square is nothing but plus a square. Because minus into minus become plus. So that what happened? 1 by 2 m into omega square into a square minus 1 by 2 m into omega square into again a square, because minus a square is again what? A square only. Then again it become what? These two are the same term. Subtraction of the same term is 0. Again it is the minimum. Again it is minimum. Now at here it become what? The minimum. Like this. Okay. Like this it will come like this. Okay. Then another one is, one thing right here, it is minimum and it is at t by 2 and T by 2 is here, it is maximum, then it is minimum. I'll write here. Next, if y is equals to what? Again it becomes 0 at here. Then it is the minimum condition. Then kinetic energy is again what? 1 by 2 m into omega square into a square is there. Then it become what? The minus. Like this. This is the graph of the kinetic energy. This is the graph of kinetic energy. If the displacement is 0, then kinetic energy is maximum because velocity is maximum. So like this. After that, we have to, the next part is the potential energy. It means the other type of the energy, that is the potential energy. We have to derive this potential energy equation. This is very, very important. The potential energy of a particle executing simple harmonic motion. Simple harmonic motion. If you want to derive this potential energy, we have to take the work done. Here the potential energy and work done both are same here. Or energy and the potential work both are same. Already you derived in that work, energy and power. That work is nothing but the change in kinetic energy. Already derived. So energy is nothing but what? The work done. Here the potential energy is nothing but what? We have to derive the work done. But one thing, I'll take the one example, that is a spring. I'll take the one example here. The spring is there. This is nothing but the potential. First, I'll write the definition. Definition. It is the energy. It is the energy. Energy by the virtue of. The position of a particle, or considered as a displacement here. Okay, by the virtue of the displacement, or it is also known as a what? Considered as a position of particle. Okay, this is the potential energy. Okay, it is nothing but what? The amount of work done by the particle, or by the force when it is moving from one point to the another point is there. The potential energy, it is also defined as here, the potential energy is the amount of work done by the force to move a particle from one point to another. I'll write a simple definition here. I write a simple definition here. Okay. It is nothing but what? The potential energy is nothing but what? The total amount of work. We have to take the total amount of work. But its total amount of work is nothing but what? The integration of change in work done. I already told that, taking one example, that is the spring. Okay. Here initially, if the particle at the initial point only, there is no motion of that. It means what? It is at the same position continuously. Its displacement is not there. It means what? The work done is also what? 0 at that position. If it is moving from its initial position to some distance, the displacement is there. If the displacement is there, the amount of work is done by that particle. It is the amount of work is W. Totally, it is W. It is total amount of work. Okay, I will remove this one. Then, because we have to derive that potential energy. First thing, one spring, take one example, okay? If it is a spring, this is a smooth table is there. One spring is just attached to a mass, that mass is there, that is called M, okay? M is a mass of a body. Okay, if there is no any force is applied on this body, its displacement is 0. Consider that x equals to what? 0. Displacement is there, na? Consider the x or here y. We have to take the x only because the x component, that's why. Displacement. Okay. Consider this displacement as a y equal to 0. When you apply some external force, or if you just pull that body, or if you push the body, it's this one. If you just push like this, okay, I'll write the second diagram here. If you just push the body like this body can take the another position. It will take the another position as compared to its initial position. It displaced how much? Y displacement. Y displacement, because you applied some external force that is nothing but F external. I will write here F external force is there. This body is displaced from its initial position. Its displacement is what? Y. Y is there. If you just push like this, if the external force is just removed, it repeats its initial position and displaces the same displacement at the another side. At the another side is there. It means the spring is just elongated. The spring is elongated like this. Now the spring is just elongated like this. It means what? It is an initial position. Now this body repeats its initial position, means it is moving like this. It repeats its position and comes the same displacement as compared to initial. Okay, the same displacement is covered by the body. It is y from its initial position. Same position is displaced by the particle here. The same. It means what? Here, when the external force is removed, it comes back to its initial position and covers the same displacement in the another side. It is due to what? It is due to the restoring force. Here, the restoring force is the opposite, equal and opposite to the external force. We have to write here what? The external force and restoring forces are there. The restoring force is equal in magnitude but opposite in direction here. Always this one. Or you can take the restoring force is equal to this one. Okay. Or you can take the restoring force is equal to minus of external force is there. But according to the definition of this restoring force, according to the definition of this restoring force here, what is that? What is that? Here, one very important point is here at this position. Here, it is continuously oscillating. The restoring force. The restoring force is always directly proportional to what? The displacement of the particle. Displacement of particle executing simple harmonic motion. But initially the displacement is in this direction, restoring force in this direction, but because it is nothing but what? Equal and opposite. You can take the external force, you can take this one or you can take this directly displacement. Okay. Okay, here the restoring force is directly proportional to what? The displacement of the particle in the negative direction, because it is the displacement is initially negative. Don't take this one, you can take here only. Now, this displacement depends on this one, so it is. Then this displacement restoring force is there. If you remove this proportionality sign, you apply one constant, that constant is nothing but a spring constant, that is 1. We have to take this one first. We have to take this one. After that, the work is done by the external force here. See here, the work is done by the external force, but the restoring force is directly proportional to the displacement of the body. Okay. Next thing is the potential energy. Now the potential energy is nothing but what? The potential energy is nothing but what? The amount of work. Now I'll take the potential energy as a, you can take the U or P. Okay, P or U can take it. It is nothing but what? The integration of 0 to W dW is there. This is nothing but a change in work done. Amount of work is nothing but the displacement of the body. That displacement is nothing but here like this. But the amount of work is, but the amount of work is, it means the change in work. I will take the only change in work. The change in work is what? dW is equals to what? That external force applied is constant here. Only one time the force is applied here. But the displacement, it means what? When you apply the small force, its displacement is small. Again small. It means what? This work is nothing but, work done is nothing but the displacement of the body. It is nothing but what? If you change the displacement, if the displacement is continuously changing, the work is also changing. It means what? It is depends on the displacement of the body. Now, dW is equal to this much. If external is there, nothing but okay. Now, substitute here that potential energy is equal to 0 to W F external into dy, okay, into dy. Now the potential is equals to 0 to W. F external force is here. F external force, you can take the minus of F RE, here formula is there. Restoring force into dy. Can I remove this? Okay, I'll remove this point. Okay, right here minus of RE. What is the restoring force? Restoring force is equal to minus of K into Y. This is equal to 0 to W is there. Initially 0 to W. When it become what? Dy. When it become what? Dy. This become, it is a displacement. Now it become displacement 0 to Y is there. Then you can take this one. Minus of, your restoring force is minus of Ky into dy is there. Then minus into minus become plus, it become dy. Then it is P is there. It is K is a spring constant, or it is called the force constant here. The K is there. K is outside. Integration of 0 to y into dy. Its power is 1. Integration of y dy is nothing but y square divided by 2. Because its form is the integration of x dx form is what? X raised to n plus 1 divided by n plus 1. We have to, here power is n is equals to 1 is here. 1 plus 1 is 2 divided by 1 plus 1 is 2. Then P is equals to K into y square divided by 2. Here lower limit is 0. Initial displacement is 0. Then amount of work is also 0. Then it displaces some displacement is there, it changes its position, then amount of work is also what? 0. Its amount of work is done here. Then it become what? The potential energy is equals to K into Y. Here K into Y square divided by 2 is nothing but 1 divided by 2 KY square is there. What is mean by Y? Y is nothing but the displacement of a body. Okay, it is a displacement of a body. Now, what is the value of K? We have to take the value of K. Now, call this equation number here 1. We take equation number 1. But we have to find the value of K. If you want to K here, but it's only just a small part, I will directly take, you can take the value of K, but I will derive it. Here the external force is equals to minus of restoring force. Minus of restoring force. But if you take here the magnitude of that, okay, if you take this one as a m into the acceleration of a body, it is equals to what? Minus. If you can take this one as a ky, take this one as a ky here. Then acceleration of a body is here, that is minus of omega square into a. Minus of omega square into a. Then it is equals to minus of k into y. If you take the magnitude only, it become already plus, because minus of r is nothing but minus ky. Minus to minus become plus here. You can take here the magnitude directly. Otherwise, you can take that if this is a magnitude, then these two are this is a minus. Then these two minuses gets cancelled. Then what happened? Here, omega square into y is the form. If you want to value of k here, then y gets cancelled. Then k is equals to what happened? K is equals to what happened here? The value of k into y is there, mass is also there, then its value is m into omega square. M into what? Omega square. Write the value of k is equals to m into omega square. In this equation, the potential energy is equal to what happened? 1 divided by 2 m into omega square into y square is a form of potential. This is a form of potential energy here. Okay, this is what? The potential energy. This is the potential energy. Then you can draw the graph of this one. You can draw the graph. Now the graph is there. Along y-axis you can take the potential energy, and here you can take the time is there. Okay, time is there. Here initially the time is 0, and here the time is t by 4, and here the t is equal to t by 2, and here it is the t is equal to 3t by 4. Just calculate the very simple part is there. It is a mean position. If it is a mean position, extreme position, mean position, extreme position are there. It is a negative extreme position, it is a positive extreme position. Okay? It is a negative extreme position, it is a positive extreme position, and it is a negative extreme positions are there. Now, one form is there. First calculate at mean position. If y is equal to, at mean position, y is equal to 0, then this is the minimum. It means what? That is the mean position. Then what about the potential energy at mean position? Substitute the value of y as 0. If it is 0, the potential energy is also, it means what? The potential energy is also minimum. It starts from its mean position like this. It starts from here. Then if y is equals to a, then it is what? Maximum. This equal to maximum. It is at a positive extreme position. Then the potential energy y is equal to a means y equal to a. This become what? 1 divided by 2 m into omega square into a square. omega square into a square. The kinetic energy and the potential energy both are maximum. Equation is like this: 1 by 2 m into omega square into a square. Now this is what the maximum. At extreme position, the potential energy also the maximum like this. If you calculating continuously, now your work will start here. If calculating continuously, here at negative extreme position, a is equals to minus a, y is equals to minus a, minus a whole square is nothing but plus a square. Then you can draw like this graph. Okay. If here it is maximum and here it is 0, here it is 0, and it become what? The maximum, and it become what? The 0. T is there. If it is, T is there. The graph are like this here because the energy never be negative. Energy never be negative. This is very important point, but it can be 0. These are some important potential energy and kinetic energy graphs are there. In the next class, the total mechanical energy is nothing but what? The sum of potential energy and the kinetic energy. We will discuss about that, and we will discuss about the graph of the combination of the kinetic energy and potential energy. Thank you.